In this video, we're going to start graphing in some detail. So this shouldn't seem as arduous as what I did last time, because now we have the basics down. Let's apply it to some real life problems. So I'm going to start with an example. Well, this will be all examples, but we'll go into detail on how you solve these. Here I'm given a function, f of x equals x squared times ln x. I want to answer a bunch of questions like the domain, the intercepts, continuity. I want to talk about that, etc., etc. And then I want to get a graph, and then I'll look at a machine version of the graph to see how close I came to it. So let's first start with the domain. All right, we have x squared has a domain of negative infinity to infinity. Any polynomial has a domain of all real numbers. Ln x has a domain of 0 to infinity. So what is the domain of the function itself? Well, it's going to be the most restrictive of all the possible parts domains. So while x squared can be anything, ln x, you can only plug in positive numbers. So the domain of f is 0 to infinity. So anything to the left of the x-axis will not be of interest to us. In fact, there won't be anything to the left of the x-axis. Moving on, I'll take care of range after I see the graph. Intercepts. Let's start with the x-intercepts. These are places where the function is equal to 0. Now, in order for x squared, so you can break this into two parts. X squared equals 0 and ln of x equals 0. Let's start with x squared equal to 0. For x squared to equal 0, x would have to equal 0, but the domain does not include 0. So that doesn't give me any intercepts. However, this does have a solution. What is it? Well, if you'll remember, ln is the same as log base e of x. So in order to solve an equation like this, you take e to both sides. So x is going to equal e to the 0, which is equal to 1. So I have, for my x-intercepts, I only have 1. When x is 1, y is 0, is the only x-intercept. Now for a y-intercept, there can only be one if it's a function, because it has to pass the vertical line test. What do? Well, plug in x equal to 0. I can't plug in x equal to 0 once again because the domain is 0 to infinity, so there is no y-intercept. Since x equals 0 is not in the domain, there is no y-intercept. All right, so I got all that stuff out of the way. That's kind of boring, but nonetheless, it tells us how we can operate. Next, I want to find out how the function, I guess, behaves by looking at maxes and mins, the things that we talked about. Here, I don't have a closed interval, so it's not necessarily true that the function is going to actually have an absolute max or an absolute min. If this interval were closed and bounded, that would be true, because up here you can see this function is created by the product of two functions that are differentiable. So the product function is differentiable. So let's look for extrema, whether local or not. So the easiest way to work extrema, since I do not have endpoints to worry about here, we can simply try to find out, determine where f prime of x equals 0 and f prime of x does not exist. Remember, these are the places where you're going to have local mins or maxes possibly happening. So let's start with equal to 0. So I'm going to say f prime of x equals 0. Now what was f of x? F of x was x squared ln x. Let me take its derivative. Use the product rule. So I'll take the derivative of x squared first, and I'll get 2x times ln x, plus, now you'll leave x squared alone and take the derivative of ln x, which is 1 over x. And so I'll simplify just a little bit. I like to simplify when I'm going to be using the derivative for something later on. Ln x plus x squared over x is just x. Set that equal to 0. And then I see I can factor out an x from both terms. So I got x times 2 ln x plus 1 equals 0. So I have x equals 0 and 2 ln x plus 1 equals 0. Now the x equals 0, I already know we can't do that because 0 is not in the domain. But the other piece, I can do 2 ln x equals negative 1, ln x equals negative 1/2, and then I can take e to both sides, and I'll get x equals e to the negative 1/2. Now if I want to graph the point and not just an x value, I need to plug this thing back into the original function to get y. So for the y value, we plug x equals e to the negative 1/2 into the original function. So f of e to the negative 1/2 equals e to the negative 1/2 squared times ln of e to the negative 1/2. And this does a lot of simplifying. Here, use the power rule for exponents to get that is e to the negative 1. And the other piece, the ln of e to anything will just be the exponent. So we'll get that times negative 1/2. Or perhaps an easier way to think of it is negative e to the negative 1 over 2. That's the same as negative 1 over 2e, if you prefer that method. Anyways, so I have a critical point. E to the negative 1/2, comma, negative e to the negative 1 over 2. Now what I'm going to do is start a sign chart for f prime. And I'm going to start it at 0, since that's where the domain of this function starts. And then I'm going to put this number, e to the negative 1/2, on it. The first thing I want to do is determine approximately what value that number is, since off the top of my head I don't know it. So I'm going to do e to the negative 1/2, enter, and I see it's about 0.61. So it's approximately 0.61. Now the way this works is this. We only found 1 0 on the whole domain. So what that means is this is the only 0. That means to the left, in between 0 and this number, it can't ever be 0. So what does it got to be? Either always positive or always negative, because this is the only 0. After it, same deal. It's only going to be positive or negative. So the way that we can check to see which one it is to pick a test point. So for example, I could do 0.3 as a test value. And as a number bigger than 0.61, probably the number 1 has got to be the best test value. So let's start with 0.3. I'm sure if you were inventive, you could come up with like e to the negative 1, e to the negative 2, etc., etc. But let's go ahead and plug these in. When you plug these in, you plug them into the derivative. So f prime of 0.3 equals 2 times 0.3 times ln 0.3 plus, and then it was x squared, so 0.3 squared. In fact, it was just x, wasn't it? Plus 0.3. Let me check that real quick to make sure I'm doing the right stuff. That's right. So 2x ln x plus x. Let's let my calculator do this for me. So I have 2 times 0.3 times, I don't even think you need these times. You wouldn't need it here, but I'm putting it in anyways. Times ln of 0.3 plus 0.3. Enter. It's a negative number. I don't even care what the decimal version of that number is. All I care about is that this is negative. That means the graph of the function is decreasing on that particular interval. Now, let me go ahead and try 1. F prime of 1 equals 2 times 1 times ln of 1 plus 1. Of course, if you know your natural log of 1 is 0, this just ends up being 1. Once again, I don't care other than it's positive. So this would lead me to believe that we have a local minimum right here because the graph's going down and then it's going up. So local min at e to the negative 1/2, negative 1/2 e to the negative 1. I think I like that version of it better. What I'm going to now next do is try to throw it on a graph and see how far I can get with it. Now I have e to the negative 1/2. We already know is about 0.61. Negative 1/2 e to the negative 1. I don't know what that is, so let me get a rough estimate of that. Negative 0.5, that's negative 1/2, times e to the negative 1. Let's hit enter and see what we have. About negative 0.19. So 0.6, I have some things here. Let me make this really big for a second. Roughly 0.6 is here for the x value, and then negative 1.9, this is about negative 0.2. So we're going to be slightly above that, but slightly down here. And I'll put my dot here as some sort of minimum. And so the graph is going to go, and well, I know that it has an x-intercept when x is equal to 1. So it comes in here and does this. And I know it does not have an x-intercept before that. So let me go even bigger. I'm going to erase this for a second and make it better. Negative 0.2 is really close, 0.9, something like that. And so I'm going to have something like this. Oh, let me fix that because I want that point to actually be my minimum. So maybe if I try to go like this, there we are, and then to go like this. I don't know what it's doing over there though. Now I do know the thing's positive from there on out. I do know that the limit as x goes to infinity, x squared ln of x does equal infinity because both x squared and ln of x go to infinity. So most likely this is going to come up here and just skyrocket. Maybe not as fast as I'm indicating here, but then I don't know right now what happens there. So let me see if I can get the limit as x goes to 0 from the right. The limit as x goes to 0 from the right-hand side of x squared times ln x. What can I do with that? I really don't have the ability to do anything with it right now. Let's see if I divide by that. I have to use an advanced thing, so I don't know. So if I really want to find out what it's doing, what I'll do is take, go back to the grapher, y equals, let's put x squared times ln x. And I want to find out what happens near to 0. So I'm going to go up to my table set, and let me set the start at 0, and I'll leave these small increments in line. So let's take a look at the table values and see what we have. It's not going to be defined for 0, but I see, if you look at these other numbers, while they're negative, they are very close to 0. E negative 9, E negative 9, E negative 9. So it leads me to believe that what we have here on the graph is a hole at 0, 0. So there's a hole. And then over here, we had our local minimum, which actually turned out to be an absolute minimum, didn't it? That point there was e to the negative 1/2, and then we had negative 1/2 e to the negative 1. So that thing there is it is both a local and absolute minimum. Not only that, we now know that the absolute minimum value is this negative 1/2 e to the negative 1. Negative 1/2 e to the negative 1 is the absolute minimum value. Now, I really can't do a lot more than this right now, but I'm going to go ahead and have the computer graph it and see how close I came. Let's throw it in and see what happens. And there's my completed graph done with the computer. Let's take a look at how they compare. I have a hole here which the graph wouldn't have known. This computer doesn't know it unless I actually try to evaluate it at that point. So there's actually a hole there. I can actually improve the graph given by the computer. We can see I'm right at about the right. These numbers were all about the same. I'll be honest, the shape of the graph after that, since it does go to infinity, it could do so in a lot of different ways, and we don't have enough ammunition right now to be exactly careful in how we do it. But I do want you to see something else. We'll actually learn something as we go forward. Let me zoom in as much as I can possibly zoom in here and see if you can see this or not. That's about as far as I can go. But what actually happens in the graph is that this graph actually goes a little bit horizontal and then it dives. What I'm saying is there's a little wiggle in here that you don't know about yet, but we'll find it as we do more stuff. Let me put my hole back and then shrink you back down. So this is the kind of stuff we're going to be doing with these kind of functions. We'll finish it off by this. Where is the function increasing? Well, what interval is the function going upward? Well, it starts at the lowest point here starts when x equals e to the negative 1/2. So from e to the negative 1/2 off to the right, off to infinity, the graph is increasing. So I will put that down there. E to the negative 1/2, comma, infinity. Where is the function decreasing? Well, that one's easy. That's what's left over here. 0 to e to the negative 1/2, not including 0. In fact, we'll do this in more detail too. There'll be something like concavity and stuff like that that we'll talk about later on. But when you list these are x values. So because x is the independent variable, it kind of drives everything that happens. We let x describe the intervals over which things happen.